Okay, so we're on the third study unit, and the topic is distributed software engineering. We will cover the following outcomes. So we should be able to demonstrate an ability to identify, analyze, and evaluate various key issues that have to be considered when designing and implementing distributed software systems. Have a thorough understanding of the client-server computing model and the layered architecture of client-server systems. Demonstrate an understanding of various commonly used patterns for distributed systems architecture, and have a thorough understanding of how the types of system to which each architecture will be applicable. And then have a thorough understanding of the closed software as a service and how it provides web-based access to remotely deployed applications. Okay, so when you talk about a system, it's important to remember that a system consists of multiple applications. It's a whole ecosystem, okay? And we have personal systems which run locally on someone's personal computer or workstation, okay? Then we have embedded systems that run, they control hardware, and they run on a single processor, okay? And then we have distributed systems, which is our focus for today's topic. And distribution systems where the system software runs on a loosely integrated group of cooperating processes linked together by a network, okay? And to further elaborate on the distributed system, it's a collection of independent computers that appears to the user as a single coherent system. So the user doesn't normally know that the system that they are using is distributed, okay? They just click a few buttons, they just use the system. They're not even really concerned about that, and they don't get to see what's behind the architecture. So as much as we say distributed systems are decentralized, but in actual fact, they still operate in a very centralized manner. The term decentralized normally also is associated with the fact that there's multiple sites of processing, and in the next slide, I'll show you what I mean by that. And information processing is distributed over several computers rather than confined to a single machine. With the typical client-server architecture that we know, or the two-tier architecture, there will be the client, and then there will be the server, which is in charge of managing resources and providing the processing power. The client or just the terminal to the server, okay? So distributed software engineering is therefore very important for enterprise computing systems, okay? Enterprise, very big organizations with a lot of users. If you're gonna expect in a particular enterprise to operate in a typical client-server manner, then the server can end up being overwhelmed. So you can see the use of having distributed systems to add that additional processing power. And as you can see, and this is just a drawing of how this kind of setup will work, the network is very instrumental in the distributed network because it connects all of these different processors together, okay? As much as we still have what we can call workstations and personal computers, we can call them as clients. And then we have these file servers, login servers, print servers that manage the resources. But the difference here, as opposed to the typical client-server architecture, is that all of these workstations and all of these personal computers, they'll bring about processing power, storage power as well, and memory, built-in memory. So the computers are independent in that sense. They're able to sort of process their own transactions and do their own work. Just imagine if it was the opposite and all of these particular clients were reliant on the server. It will take up a lot of resources and the network may end up being slow. So some of the characteristics that come with implementing distributed systems, it ensures resource sharing, okay? So memory of the server is not compromised and put under pressure because there's resource sharing, there's balancing or load balancing. between the various machines that make up the system. And openness as well. In a distributed system, we have a wide variety of hardware and software usually from different vendors. So there's that whole concept of being open. Okay, it doesn't really matter because you can sort of bridge it somewhere using some middleware. So there's different platforms as well and different vendors of hardware and software. There's also concurrency. And the concept of concurrency means an ability to execute multiple transactions at the same time, okay, without experiencing any performance issues or conflicts. So for the mere fact that there is localized processing, it means as many of the transactions as possible, the computers can independently execute them by themselves. And then when they need additional resources, then they can consult with the server. Also, scalability. As the organization grows, then you can add additional processing power through adding new workstations and personal computers, okay? And so it's good for that aspect of scaling. And also fault tolerance. Although it is a bit difficult to troubleshoot, but its design in terms of distribution, a distributed system is fault tolerant because if one of the computers go down, since there's independence, it means it won't really affect the other computer's ability to continue functioning. Okay, even if the server goes down, it means the other computers, it's just that you won't be able to access most of the resources, but your localized computer will still operate, will still be able to store data, will still be able to do some sort of processing, okay, for as long as the internet is not affected. So what are some of the issues that you experience with implementing these distributed systems? They say they're very complex, okay? They're more complex than systems that run on a single processor. And the complexity arises because different parts of the system are independently managed, as is the network. There is no single authority in charge of the system, so top-down control is impossible. We know in the two-tier architecture, client architecture, it is top-down, and who sits at the top, or what sits at the top rather? It's the server. And everything else has to be compliant, and the policy is ensured at the server level. Here, there is no single authority, okay? Each particular computer has a say, and that's what makes it so complex that it's difficult to manage. So some of the design issues, again, goes back to some of the benefits. The benefits can also be the disadvantages, and they can be a challenge as well. So transparency, when we talk about transparency, to what extent should the distributed system appear to the users as a single system? Because as much as we want the distributed system to sort of operate like a single coherent system to not compromise the user experience, but to some extent, you do get delays and you do get performance issues, and then users will start to question these performance issues. So try to, as much as possible, although it's a distributed system, but the user must not be able to see that, okay? You must not be able to experience that. And should the system be designed using standard protocols that support interoperability, okay? That aspect of openness as well is what's going to be questioned. Do you want to go on one platform, or do you want to go with different platforms, okay? And that's one of the questions you may need to ask yourself. How can the system be constructed so that it is scalable? How can the usable security policies be defined and implemented? How should the quality of service be specified? These are just some of the questions that you're going to be asking yourself, and these link back to some of the design that we mentioned in the earlier slide, that the distribution characteristics. And then we have the middleware, okay? So the components in a distributed system may be implemented in a different programming language or different programming languages, and may execute on completely different types of processes. Middleware is software that can manage these diverse parts and ensure that they can communicate and exchange data. So the middleware in any system is a translator, okay? It's there to bridge and convert from one language to another. So here we are, we have all of these different applications, and we can assume that computer 2 and 3 share the same platform or operating system, and then we have computer 1 and 4, which is a different operating system. So we need the middleware to be able to take the data being generated by these different computers and the applications and convert it into one standard format that we can store in a database, that we can store on the network, okay? So that's the role of a middleware in a distributed system, is to bring consistency, okay? As much as these different workstations can be running or speaking different languages, but we need common ground, okay? Because remember, they all build to this whole thing that we perceive as a single coherent system. They're contributing to the single coherent system. So somewhere along the line, they need to be talking the same language. And so when you talk about client-server computing, distributed systems or accessed over the internet are normally organized as client-server systems. So distributed systems are client-server systems with multiple layers in them, okay? Unlike the typical two-tier one. So in a client-server system, the user interacts with the program running on their local computer, example, a web browser or mobile application. This interacts with another program running on a remote computer, which we refer to as a server, right? And that's typical 3-layer architecture. The remote computer provides services such as access to web pages, which are available to external clients, okay? And speaking about clients, we can have thin clients and then we have fat clients. So what is the difference? You can see on the screen in front of you now that the one on the right is an example of a thin client. And another term for this is a dumb terminal, okay? Because all it does, it's a terminal to the server. It doesn't have a processor. It doesn't do any storage, okay? And that's all it does. It just connects and consumes from the top down structure, which would be a server. And then when it comes to the fat clients are the ones that you typically see in a distributed system because they have the ability to work or operate offline or work independently to some extent through processing. So the processing power is not solely left to the server to do, okay? And they say the fat client model, where some or all of the application processing is carried out on the client, data management and database functions are implemented on the server. So there's a bit of a balance between the two. So if you are using the thin clients, then this is how your architecture would look like, okay? The squares will represent the server, and the circles will represent the clients, and the different clients will connect directly to the server. When it comes to the actual systems themselves or the softwares that you use, if you're working with a particular application that is two-tier, there is no reuse there, and it makes it difficult for you to separate the business logic layer from the user interface to the data logic layer, okay? So hence, a solution was required, and they needed to improve from two-tier to make life easier. They needed to improve from two-tier, and they moved on to the next one, which is three-tier. Okay, so how is three-tier an improvement? You can see now it's very easy to reuse the systems we build because we separate the different layers. And so if you wanted to rebuild this application again, you just take the bottom two. I'll just move on to the next slide because it shows us an example of an application that you could see in three-tier architecture. So we have internet banking. Let's just imagine this was an internet banking system. and you on the client, which is a web browser, you're browsing the internet banking system, and obviously it's using HTTPS protocol because it's web technology. So you access it, and then you would be making requests to scripts that are hosted on a central or remote machine called a web server. Okay, so this would be your first tier. Your first tier is your web browser, the presentation, what you see with your eyes. The second tier would be the tier that has the business logic or the code, the scripts, okay, the server-side scripts. And then you have your third layer, which is the database layer. And this is where all of your SQL queries are executed against the third layer, okay? So here we are able, unlike the two-tier architecture, with three-tier, there's better reuse, okay? You saw in the previous slide why I say so, because you can just reuse the script on the web server and the database, and then change or tweak the presentation layer, which is the first tier. So then we moved on from three-tier, and now we have something called N-tier, because they realized that different organizations may have different reasons for adding additional tiers or additional layers to their systems. And the improvement from three, the significant difference between the third tier and the N tier is that here they included an additional layer for security validation purposes, okay? And they refer to it as the data handling layer. So it's not enough that you do your validation at the presentation layer. Some systems analysts or people who build systems or developers tend to do validation at presentation, which is good. And this is called client-side validation. If you're going to validate using the web browser only, you're exposing the rest of the system to threats because it can be overridden, okay? So somebody can turn off JavaScript on the browser, and then your whole validation process is now compromised. So validation at presentation layer alone is useless. Someone is always smart enough to get through it. So there needed to be a different layer than a data handling layer. And the sole purpose of this data is to ensure that the data is clean and in a format that it should be in. Okay, so if you are capturing the email address of someone, then the data handling layer will actually validate whether the structure of that data does actually represent the email address. It doesn't mean it ends there. It continues, okay? After the data handling layer, then you move on to the application processing layer, and there as well, we would do some sort of validation. And this is also purely referred to as the server-side validation, okay? So you would use your Java and you would use your C# to validate the structure of the email address. And also at the database level, you can enforce validation there as well by ensuring that the particular field or column in the database table does conform to the particular data that you want to store. So if you wanted to store a cell phone number, by making it an integer would be one of the. I don't think there's a direct way of enforcing a cell phone number on a database field, apart from just making sure that it's numeric at least, and you've just put in a measure to reduce any malicious intent. Okay, so those are the different ways, and that's why they keep adding additional tiers. It's just to make the system more trustworthy. And this is basically describing what was in this diagram, what I just spoke about now. So we have these different architectures that we can use to implement a distributed system. And we have what we call the master-slave architecture, which is used in real-time systems in which guaranteed interaction response times are required. One such example would be if you're building a system that's going to be used by the plane or aeroplane, okay? Remember, aeroplanes are equipped with external sensors, and these devices are mounted on the plane, and they are meant to pick up maybe change in weather conditions, change in altitude, and so forth. So when it comes to the master-slave architecture, we have these different servers sensors rather, they're picking up in real-time signals and they're reporting to a centralized location, which is probably the computers in the cockpit. So that's how a particular master-slave architecture would work. It's all for real-time communication. And then also two-tier, which we just spoke about. It's a simple client-server system, and where the systems is centralized for security reasons. And this is where in the two-tier, it's where we said we have the top-down approach, where the server holds the highest ground. And then the multi-tier and the N-tier, which is used when there's a high volume of transactions by the server, and you need the additional workstations that have the capabilities to do localized processing. Okay, so this multi-tier client-server architecture is the one which you can take and convert to what we call distributed components architecture. Okay, because with the multi-tier architecture, we can ensure that there is some sort of local. We saw that we tend to use the fat client as opposed to the thin client when implementing a distributed system. So distributed component architecture, which is used when resources from different systems and databases need to be combined, or as an implementation model for multi-user client-server systems. And then lastly, we have the peer-to-peer architecture, okay? I'll just save the peer-to-peer for the next slide. So when a system is computationally intensive, and it is possible to separate the processing required into a large number of independent computers, it's advisable to use peer-to-peer. When a system primarily involves the exchange of information between individual computers on a network, and there is no need for this information to be centrally stored. So peer-to-peer means we do not need any central authority. We do not need any server. The computers will directly, they are fully independent. And if they need something, they'll directly communicate with one another. It's a very risky way, obviously, of managing data. You're giving too much authority. You know, with the distributed architecture, you ensure that you strike a balance. But with the peer-to-peer, it's purely independence, okay? And there are various concerns that you may have here, especially pertaining to security concerns, okay? So security concerns are the principal reason why peer-to-peer architectures are not widely used. The lack of central management means that malicious nodes can work to set up and deliver spam and malware to other nodes on the network. So you need to trust the other nodes on the network, because if one computer does not have, for example, up-to-date antivirus, then it compromises everybody on the peer-to-peer network. Peer-to-peer communications require a careful setup to protect local information, and if not done correctly, then this is exposed to, or it exposes rather, the other peers. So what you need to take out of this is that when you're talking about the concepts of distributed systems, it's because we need something that's able to scale as our organization grows, okay? And we've acknowledged the fact that the normal two-tier client-server architecture systems do not serve the purpose. So we need to move on to something that could relieve the stress from the server, which is distributed systems with localized processing, which brings us to the next concept, okay? So we know peer-to-peer is definitely unsustainable, and it's not an option for a big organization. You can use it if you're a small organization and there's not much of a risk, okay? So peer-to-peer is definitely out of the picture. You have an alternative. If you cannot afford to implement the infrastructure yourself within the organization, but you are concerned about your growth, then you can opt for software as a service, okay? And software as a service involves hosting the software remotely and providing access to it over the internet. Software is deployed on a server and or more commonly, number of servers, and is accessed through a web browser and is not deployed on a local PC. So people access it remotely through internet and the web browser, and it's not like your typical distributed system where you have something that is, or a client that is installed on your local computer. The software is owned and managed by a service provider or a software provider rather than organizations using the software. So if you are using a software as a service, you're not owning, you are renting. That's what you must know. So you limit it into what you can and cannot change. Users may pay for the software according to the amount of use they make of it or through an annual or monthly subscription. So there's different subscription models that the different service providers offer companies. The most popular one, obviously, is monthly subscription, where you pay monthly and you bill at the end of the month. So your bill may not be the same during the time where you are experiencing heavy traffic. Then they would adjust your resources for you. So you pay more during those months, which makes it an alternative to a distributed system because you are now letting someone else handle the risk, okay? The risk in terms of bandwidth and so forth. And as already mentioned, the key elements of software as a service. So implementation factors for software as a service, and these are some of the things that you need to take into consideration. Configurability, if you need something that you're going to configure a lot, then software as a service is not really for you. I tend to use the example of living in a sectional title versus buying a standalone house. If you buy in a sectional title, there's certain things you can do, but we agree that it has its benefits, better security and so forth, but there's certain things that which you cannot do to the unit, although you own it. But when it comes to a standalone house, you have the freedom to do whatever you want, make changes, renovations on the outside. So that's the same thing that works. That's the same concept that applies here. If you're choosing to have a localized distributed system, you can make changes as you want. And configurability becomes an issue when it comes to software as a service because you are renting. So don't implement that solution when you want to make a lot of changes. Also, multi-tenancy. The fact that you are a tenant and there's other tenants as well, it means there are certain boundaries that you need to respect, okay? And you cannot be selfish in terms of trying to hog the resources for your particular organization. And scalability, how do you design the system so that it can be scaled to accommodate an unpredictability of the large number of users? And in terms of configuration, you can just look at this as a picture. We have all of these different companies. They will all have different requirements for their users, okay? And also they will all have different users. So you can see company C is it's smaller than company 1 and 3. But every company would, in terms of software as a service, would come with their own, they would want their own profile there, and they would all come with their own challenges, okay? And that needs to be taken into consideration in terms of configuration purposes. So configuration covers these following points. So branding, you buy this or you rent this software from this organization, but how do you brand it and make it speak to your customers? You may want your colors there. You may want your logo there as well. So that becomes one of the concerns. Also, business rules and workflows, okay? Even companies that are in the same industry have their own unique set of business rules of what customers can and cannot do and what employees should do when carrying out a service. So how do you take this generic solution, software as a service, and make it speak to your business rules? And also database extensions. You may have additional database tables or database needs that you have as an organization, or you may want to segregate different sets of data. So that software needs to allow you to do that. Okay. Sometimes you may want to bring your own database. And what if the software provider already provides you with the database? Then what do you do? Now you have to face with a situation where you have to migrate data from the old structure into this particular service provider structure. And also access control, where service customers create individual accounts for their staff and define the resources and functions that are accessible to each of their users. Okay, this is also an important thing. You want access control. You want different roles implemented for different users in the organization. Okay, and to what extent the software as a service solution provides you that with those capabilities remains at their discretion. Okay, some of them do understand that obviously in any organizations there's different levels of management, and there will be requirements for different permissions. So those will normally come as part of the package. So again, the whole concept of multi-tenancy is a situation in which many users access the same system, and the system architecture is defined to allow efficient sharing of system resources. We have the multi-tenant solution, and then we have the single tenant solution. We can say that the single tenant one is the most efficient one, but it's also the most expensive one, okay? Because there's a dedicated application and a dedicated database for each of the company profiles. However, with the multi-tenant solution, the different companies are sharing the same application, just with their additional branding configurations, and the data goes to different databases. But for the fact that they are sharing the same application means that this particular solution would definitely work out to be cheaper. Okay, so in conclusion, designers of a system must carefully choose the most suitable architectural pattern, and this should be done on the basis of considering performance, dependability, security, and manageability of a system. Distributed systems are also known as software as a service, and software as a service can be defined as a cloud computing service where several servers may gain access to the services provided in the cloud. Okay, so that is study unit 3, all about distributed systems, and it can be a big challenge to implement, but you do not have to do that yourself. You can opt for the cloud, which is what most organizations are doing now. And also by using the cloud, you sort of taking away all of those concerns when it comes to security, because remember that the cloud service providers, they've been in this industry for a very long time, and they can definitely implement these solutions better than you can. And they have, if you picture organizations like Microsoft and Google and stuff like, they have so many servers and so many resources to implement the solution better than you. So software as a service, if you can afford it monthly, is better. It's definitely the more attractive solution to solving this problem of scaling, because what I see here, the bigger picture is scaling. How do we ensure that our network and our computers can accommodate the number of users if we are a growing organization? Okay, so that is study unit 3. And would you guys have any questions regarding this particular study unit?